Hello, everybody. This is Sunday. It's January 15th, and we are moving into week 2 of our online astronomy course. Now, I want to remind you that next Monday, not Monday the 16th, but Monday the 23rd is when your first 2 modules are due. So you'll have to have the homework for the first 2 modules done. I've given you 2 weeks for module 1 to give you time for your textbook to arrive. But after that, we'll have 1 module a week due, except for spring break. And over spring break, we'll just take that week off and you won't have anything due. So, module 2, we're going to be talking about earliest attempts to understand motions in the sky. And here you can see behind me, I explained last time that this is taken out at Summit Lake in Lassen Volcanic National Park in Northern California. I took this about, oh my gosh, 2016, that's 7 years ago, isn't it? Yeah, about 7 years ago. And we're looking south here. You can see the bright light over my shoulder is the lantern that's in my tent. And you can see all the stars that were out on this moonless night, beautiful night, so many stars. And over my shoulder, you can see the Milky Way right here. That is our Milky Way galaxy, and we'll be talking about that much later in the course. But there's also 2 other objects here in the sky. There's 2 planets visible, and those are over on the right side of the screen. Those are Mars right here, and then Saturn right here. Earth rotates on its axis, and we know that causes stars to rise in the east and set in the west. And I'll remind you, we are looking south here. And so if you're looking south on your screen, over on the left side of the screen is the direction of east. So over here is east. And in the other direction, other side of your screen is west. So stars rise in the east, and as Earth rotates, the stars appear to move from east to west. Now, the Greeks and the earliest people who thought about this thought that Earth was motionless, thought Earth didn't rotate on its axis, thought it didn't orbit the sun. They thought Earth was the center of everything. Everything revolved around Earth. So they saw, or they imagined, that Earth was surrounded by a giant globe that held the stars, sort of like a planetarium. And we're looking at the inner surface of that planetarium that held all the stars. And that planetarium would move, that celestial sphere would move and rotate from west to east. Now, if you think that's backwards, oh my gosh, I thought, stars rise in the east instead in the west. But if Earth isn't spinning and the celestial sphere is spinning instead, the celestial sphere spins in the opposite direction that Earth really rotates in order to get the stars appear to rise in the east and appear to set in the west. If you think of yourself on a chair that can spin around, and if you spin around in this direction and you just look straight out, it looks like the room is spinning in the opposite direction. And that's why from our rotating point of view, we see the stars appear to spin in the opposite direction that we're spinning. So the ancient Greeks began to figure things out, and they knew how big Earth was. There was a man named Eratosthenes, and he figured out how big Earth was by noticing the changing angle of the sunlight the changing angle that sunlight would come in as you walked north and south on the surface of the Earth. And he got a very good value for the size of Earth. So even the ancient Greeks, and this is in a couple hundred years BC, knew the size of Earth. And in fact, on one of your optional observing projects, you will make observations like Eratosthenes did and measure the size of our Earth. Now, they knew the size of Earth. During a solar eclipse, Earth casts a shadow on the moon. And they could compare, looking at how big that shadow was on the moon, they could compare that. They knew the size of the shadow. It's the size of Earth about. And that means they knew about how big the moon was. Now, you know that as something moves farther and farther away from you, for instance, if I take this little ball here and I hold it close to the camera, and then I move it further and further away from the camera, it looks smaller and smaller and smaller. Things look smaller as they get further away. And so the Greeks were able to figure out how far away the moon would have to be to look as small as it does. They knew the moon's true side from the eclipses of the moon. They knew how big the moon appeared to be. And so they used that to figure out how far away the moon was. And so they knew an awful lot. They knew the size of the moon. They knew how far away it was. They knew the size of Earth. But that was it. The size of the sun, let me see, the size of the sun and the distance of the sun had to wait for about 1,500 years for people to begin making progress on that. In fact, they had to wait until about 2,000 years to make progress on that. So the Greeks were very clever, very smart, but they could only take things so far. Now, but it was important to them because they practiced astrology. The Babylonians practiced astrology even before the Greeks arrived on the scene. So astrology is a very old practice, and it looks for patterns in the sky, looks at the motions in the sky, and tries to predict where things are going to be at a certain time, and so forecast the future. It's something they did. If you want to look up your horoscope in the daily newspaper, that's fine, but it's of no proven worth. But if you want to do it for fun, go ahead. But they made models, mathematical models of how things moved in the sky. And they wanted to know where the planets were going to be in the sky. And most of the time, planets would move from night to night against the distant background stars. Planets would move from west to east. So I'm going to start out a planet. I'll let this little ball here be a planet. I'll let it be Mars. Just put it over Mars there. And from night to night, if I go out at the same time the next night, it would see that Mars moves a little bit to the east. And then the next night, a little bit to the east. And then the next night, a little bit to the east, as it drifts against the distant background stars. So the stars aren't changing their position. It's the planet that's moving against the distant background stars. And so from night to night, Mars and all the planets would move from west to east. Now, they thought that everything orbited Earth. And it makes sense. If something is orbiting the Earth, then it's only going to move around you in one direction. Just like this is moving around me. And when I look at it, it only goes around right across me as it moves in a circle around me. And I'm always looking at it. So I always see it going in the same direction. Namely, here it goes, and I see it going that way. So that makes sense if planets are moving that way. And In fact, they believed that all motion had to be circular. Why? Because a circle is the perfect shape. And so all motion had to be circular. But they quickly found out that the planets did not move always from west to east. Okay. From west to east, this sort of motion from west to east is called direct motion. But sometime a planet like Mars here, say, you would see Mars from night to night to night to night, going to the west all the more, and then it would slow down, and then it would reverse direction and go to the west, backwards. And that's called retrograde motion. And then once again, from night to night, it would travel to the east through the distant background stars. And what can cause this? Oh my gosh, to try to figure this out, just drove them crazy. It was a terrible problem. What are these, objects that they knew about? They knew about Mercury, they knew about Venus, they knew about Mars and Jupiter and Saturn. So they knew about the 5 planets and how the 5 planets move through the sky. And they didn't always move from west to east like they should. Sometimes they moved backwards from east to west in retrograde motion. And in fact, the very name for these objects, planets, is the Greek word meaning wanderer. And so the Greeks called these objects wanderers because they would wander through the sky, sometimes going forward, most of the time going forwards, but sometimes going backwards, and so on. Well, they really wanted to understand this, and they wanted to be able to predict for their astrology where the planet was going to be. And so there was a man named Ptolemy. Now, there were some earlier people who had Ptolemy's ideas, but the precursors to Ptolemy's ideas, but Ptolemy really perfected them. And he said, only circular motion is allowed. And so here's a planet, and that planet is going on a big circle around Earth. Now, the planet is really going to be on a smaller circle. And it's the smaller circle. You can see the planet is, let's start it over here. Here's the planet on that on that smaller circle. And it's the center of that smaller circle that's going to move around Earth. And as the planet is on that smaller circle, the planet goes through circular motion on that small circle. So the planet is going on a small circle as the center of that planet is being carried along a larger circle around Earth. The small circle is called an epicycle. The large circle is called a deferent. So let me see if I can show you that. I'll try to start over here. This is going to be hard because I'm going to have to swing my arm. So basically, I'm always pointed toward the camera. Let's see how well this works. So it's going like this. And this is if the center of the circle is not moving. The center of the circle is where my fingers are. You can see, if my fingers are not moving, if the center of the epicycle is not moving, then sometimes the planet goes forward and sometimes it goes backward. Forward to the east, backwards to the west. But if that circle is being carried, from west to east, if the center of the epicycle moves from west to east, then this planet will experience retrograde motion. Most of the time it'll move forward because the center of the circle is moving forward. But sometimes the motion around the epicycle carries it backwards. So let's see what that would look like. I'm going to start over here. And this time we're going to view this epicycle from the side, because that's what Ptolemy sort of envisioned, looking at that epicycle from the side. So I'm going to move the planet like this. And then I'm going to try to move my hand across the screen. So in this case, my hand is just going to carry that circle across the screen. So let's see what happens. Carry that circular motion across the screen. I'll try to do it at a constant speed. You can see there's sometimes that the planet moves backwards against the distant background stars. Let's try that one more time. See if I can do that again. Going to move it a little bit further back so you can see it better. Here we go. There's back, retrograde, so on. And so this system of epicycles moving on a deferent around Earth was Ptolemy's scheme for how the solar system worked. And Ptolemy lived about 100 to 170 AD. No, you don't have to know dates. I'm never ask you dates in here. And this was a spectacularly successful system for predicting the motion of the planets. And it was so successful, in fact, that it lasted for about 1,200 years. So 1,200 years of people believing this is what the solar system looked like. Now, Ptolemy himself didn't believe it. This was a mathematical model for predicting the positions of planets. And it worked very well. He had different sizes of deferents and epicycles for every planet, and they would spin at different speeds. And they managed to really do a great job of reproducing where the planets were. He had to make some alterations, some adjustments to his model, but it really worked well. But his followers took this to be the truth, that there were really spheres out there that held these epicycles and deferents, and they all rotated, these crystalline spheres. They had to be transparent because we can see the stars through them. But he talked about these crystalline spheres, Ptolemy's followers. And every time, in the old, maybe you've been to Prague or some city in Europe where they have a really old clock in the town square. And you can see at the center of all those clocks, there is the Earth, and moving around Earth are the planets. And so the idea of a Earth-centered solar system, a geocentric solar system, was really ingrained in everybody's basic belief about how the world works. So that lasted, as I said, about 1,200 years, until a man named Nikolai Copernic took stage. And Copernic was a Polish lawyer. He was a physician. He was a mathematician. But basically what he was brilliant. And he wrote papers talking about his thinking. And in those days, you would write all your scientific papers in Latin, and you had to take a Latin name. And so Nikolai Copernic became Copernicus. And Copernicus said, I can explain things just as well as Ptolemy's system can, but much easier, much simpler system, and just as accurate. And Copernicus came up with the idea of no, Earth is not at the center of the solar system. It's the sun that's at the center. And all of the planets orbit the sun. So where does retrograde motion come from then? No, Copernicus said, get rid of those epicycles, get rid of those deferents. No, what happens is that all the planets are orbiting the sun, and when we are closest to another planet, we pass it by in its orbit. And when we're passing it by, that planet appears to be moving backwards. It's just like if you're in your car and you're waiting at a traffic light and there's a car behind you, and you move forward faster than the car next to you, that car appears to be moving backwards through your window. So the planets aren't actually moving backwards. They're always moving in the same direction in their orbits. But when Earth is closest to those planets appear to be moving backwards. And that's retrograde motion. How much easier is that? So Copernicus got it half right. Yes, the sun is at the center of the solar system. We have a heliocentric solar system, but he still used circular orbits. And he still didn't know how far away the sun was. And so when he made his model of the solar system, he had to say, well, we'll just pretend, we'll call the distance from Earth to the sun 1 astronomical unit, 1 AU, astronomical unit. And then he gave all the other distances from the sun in terms of the distance between Earth and the sun. For instance, Mars is 50% further from the sun than Earth is. And so Mars' distance from the sun is 1.5 astronomical units, 1.5 AU. Venus, on the other hand, is closer than the sun. I'm sorry, closer than Earth is to the sun. And so the distance from the sun to Venus is 0.72 astronomical units. So we knew the relative sizes of the orbits, but we did not know their actual physical sizes in meters or kilometers. But Copernicus really, I mentioned the little adjustments that Ptolemy had to make to his model. It turns out that Copernicus had to make little adjustment to his. And they really didn't make a lot of sense. So Copernicus, as I said, only got 50% of it right. Got the sun at the center, but he still had the orbits circular. And it was up to a Polish mathematician. I'm sorry. Gosh, I should know what Kepler, I think he was also Polish. But Johannes Kepler was the next to arrive on the screen. Copernicus, by the way, was afraid of publishing his idea of a heliocentric solar system with the sun at the center because the church, he was afraid, was going to call that heresy and try to punish him. Now, he lived way north of Italy where the Catholic faith held sway, but still, he was very worried about it. There was still Catholicism going on in the north. And so he wrote all this up in his book, and he had it published on the day he died. And so on the day he died, Copernicus saw his book, and I think that's just an interesting sidelight. As I said, Kepler is the person who figured out the shapes of the orbits of the planets were not circular, and they aren't. They are instead slightly oval shaped in a shape that's described by an ellipse. And so planets move in elliptical orbits around the sun. And the sun is at one focus of the ellipse. Now, you may not know about the focus of an ellipse. That I'll leave for your reading to show you exactly what an ellipse looks like. But Kepler came up with an exact description for how all the planets move around the sun in their elliptical orbits. And he really worked hard to do this. Kepler was something of a mystic. And early on, he wanted to know how the planets really moved. Kepler was very devout, and he himself said, I want to read the mind of God, to see how God is really arranging the solar system. And so he looked for symbols in the stars. He thought, well, gosh, maybe the orbits of the planets, the sizes of those are like the same ratio as a triangle is to a square, is to a pentagon, and that didn't work. He was able to get close by jiggling things around, but nah, he threw that out. It didn't work. And I thought, oh gosh, maybe the orbits of the planets and the speeds of the planet are such that when the planets go around their orbits, the crystal spheres rub against each other and produce a harmonious sound. No, no. But then Kepler did an amazing thing, and this is why I really admire Kepler. And Kepler, was an astrologer. He cast horoscopes for royalty. Um, there were no real astronomers back there, and there were mostly astrologers. And Kepler moved from looking at the sky as being symbolic messages that you have to decode to looking at the objects in the sky as objects themselves. And that was a huge mental change, because instead of trying to read secret messages, encoded in how the world works, you look at the world as a collection of objects that have motions and try to figure out exactly what what that means in and of itself, and not as some message sent to us. So you don't start with the message and try to make it fit. You start with the objects and the observations, and from that, try to understand how the objects are really moving. And there's no symbols, no magic in it. So Kepler did that, and that is when astrology became astronomy, right at that time. And Kepler published a book on that. Here it is. This is his Astronomica Nova. It's a big book, and it is filled with his attempts at trying different shapes. He would try different shapes and try to understand how objects would move. And amazingly, what makes this book cool is that Kepler, as he went on, said, well, I'm going to try this. And then he put down all the math for it. He said, dang, that just didn't work. And he kept trying. And finally, he got it. He got ellipses. And for that, he was using observations made by Tycho Brahe. And Tycho Brahe lived around 1546 to 1601. He was about the same time as Kepler. And Tycho Brahe was the greatest naked eye observer of his time. In fact, for all time, because right after Tycho Brahe, the telescope was invented. So this is all before the telescope. And Tycho Brahe would make meticulous observations of the positions of the planets from night to night to night against the background stars. And Brahe was in Prague at the time, and Kepler went to see Brahe and try to use some of his observations. And Kepler was able to use Brahe's observations as well as make observations of his own. And in fact, several years ago, I was in Prague and I went to the monastery where Kepler's records were kept. And I went to a scientific museum across the river that actually had some of Kepler's instruments that he used to make measurements. And now they're behind glass cases. But back then, they were just out in the open. I mean, you could, in fact, I did. I put my eye against the tube so I could sight along that instrument, just like Kepler did. And that was just so cool. But Kepler figured out that 3 laws. In fact, he figured out 3 laws of planetary motion. First of all, planets move in ellipses around the sun. The second law was that talked about how planets vary their speed as they move around an elliptical orbit, because sometimes the planet's a little bit closer to the sun, sometimes a little bit farther away. And he described how exactly that worked. And third, he wanted to know, well, how much faster does Venus move than Mercury? How much faster does Mars move than Mercury or Venus or Earth? He wanted to find out the relative speeds of the planets. And that was his third law. And that took him a lot longer. It wasn't until I think around 1619 that was published. But those 3 laws, Kepler's 3 laws of planetary motion, describe how the planets orbit the sun, and that is our understanding today. So that is the beginning of our modern understanding of the solar system. Now, Kepler didn't understand why. You know, just think of it. Here he has this huge stack of observations that he has from Tycho Brahe. And, you know, it says, okay, one night Mars is here, then it's over here, then it's over here, then it's over here, whereas Saturn is here, and it's here, and it's here, and it's here. Then maybe it goes backwards. I mean, how do you get the shape of the orbits from that? It was an amazing, amazing feat, and I really admire Kepler for that. And ever since we've started taking the universe as consisting of objects in their own right and not as symbols, astronomy took off. It was still a scale model. We still call the distance, the average distance of Earth from the sun as 1 astronomical unit. And as I said, that wouldn't be solved till much later. And we'll talk about that later in the course. Now, last person I'll just mention is Galileo. Because Galileo came along and he made a lot of discoveries. He lived from the late 1500s to around 1640 something. And Galileo did not invent the telescope, but he perfected one of the very first telescopes that he heard of. And he ground his own lenses, and he looked through his telescope at the moon, he looked at the planets, and he made amazing discoveries. He found out that the moon had craters and mountains, that it wasn't a perfect sphere, the way church dogma had said, because everything, the moon and above, was supposed to be absolutely perfect. And a perfect moon wouldn't be blemished. He saw that Saturn, looked at Saturn, and he found out that Saturn had rings. Now, telescopes, the optics of Galileo's telescope were not real great. So he thought that he saw that the planet Saturn had ears, as he called them. And later, it was discovered to be the rings. But most importantly for us, Galileo discovered 4 moons orbiting the planet Jupiter. The 4 Galilean satellites of Jupiter, as we call them today. And that was amazing because it was proof that Earth was not the center of all things. Here are satellites, moons orbiting around Jupiter. And they obeyed Kepler's laws of motion. So the speeds of the planets obeyed Kepler's 3rd law. And so this was great confirmation of Kepler's ideas. And again, Kepler began to make experiment about why things moved on Earth. But he didn't make the connection of applying those ideas to the heavens. So Galileo was truly breathtakingly brilliant. And I'll mention that at a meeting of the American Astronomical Society several years ago, I went to Ann Arbor, Michigan, and there it was celebration of the 400th year of Galileo doing something. I'm not sure what it was, but they had Galileo's letter on which he recorded his first observations of the moons of Jupiter. And I mean, Galileo, saw that. He was astounded. And so he just grabbed the nearest piece of paper he had. It was an old letter he had written to somebody. And he made a copy of it. And he made sketches of the positions of the moons from night to night on that letter. And in fact, in the introduction to Module 2, I've put a reproduction of that letter so you can see what it looked like. But yeah, Galileo got into trouble with the church for insisting that Earth went around the sun, that we live in a heliocentric solar system. And he was convicted of teaching by a Vatican, in a trial by the Vatican. It was convicted of teaching something that was forbidden, and he was sentenced to house arrest for the rest of his life. And when he was at his house under arrest, he continued to work and did some more inventing of the very beginnings of what we today call the laws of physics. And we'll see next time what Isaac Newton did with those laws, because he ran with them and he discovered the reasons for Kepler's laws. And he discovered the basic laws that describes how everything in the universe moves. So we'll talk about that next time. Before I go, I do want to pull up Stellarium really quickly here. There we go. Here's Stellarium. The time is set for the 18th. That is Wednesday, and it is 10 at night. And you can see down here is it's scheduled for set for 2200 hours on January 18th. And we're looking north this time. You can tell by the little N down there. This time we're looking north. And if you're looking north at this time of year, do you see anything that looks familiar? How about the Big Dipper? So here is the Big Dipper. It is an asterism. An asterism is just a star pattern, and it forms part of the constellation of Ursa Major, the Big Bear. And these two stars at the end of the Big Dipper's bowl, the bowl of the Big Dipper, you can follow from this one at the bottom of the bowl. You can go through the top of the bowl, keep going in a straight line, and the first bright star you hit is Polaris, the North Star. And Polaris is the star that is directly above Earth's north rotational pole. And so it doesn't appear to move during the night. All the other stars appear to move around it. And you can tell that if I move just a minute at a time here, you can see the stars. Oops, I'm sorry, here we go. Stars do move around Polaris. For some reason, the stars aren't moving. What if I go by an hour? There we go. There, I was making too small a movement. You can see the stars moving around Polaris. There we go. I'll go backwards in time again. So the stars rotate the other way. I'll tell you that this star, this one of the pointer stars, the one at the uppermost of the bowl, that is Utah's state star. Its name is Doobie. D-U-H-B-E. I'll click on it and you can see information. D-U-B-H-E. Doobie here is the name of that star. And like many of the names of the stars, Betelgeuse and so on, they come from names that are found in old star maps annotated in Arabic. So take a look at the Big Dipper if you get a chance. It's snowing right now outside, so you may not get a chance for a couple days, but take a look at the Big Dipper and see if you can find the North Star Polaris. All right. Well, I've talked a lot about this, but this is really cool stuff. This is the history of astronomy. And next week, we'll start learning about the science of astronomy and the laws of nature that astronomers use to understand the universe. So until then, I hope you enjoy learning about this history, and I will look forward to seeing you next week. So until then, bye-bye.